Homework 18, section 8.3, confidence intervals for population proportions, video 4. I think this will actually be the final video. We're going to talk about controlling the margin of error. And in order to figure out how to do that, we need to recall where the margin of error comes from. Recall that the margin of error comes from the z-score, which we get from the confidence level, times the standard error. But the standard error comes from the square root of a fraction with n on the bottom, and on the top, p hat times 1 minus p hat. So let's think about what we could control that would make the margin of error smaller. Let's start with the z-score. In order for this multiplication problem's answer to be smaller, we could make the z smaller. But recall that the z comes from the confidence level. So I'm going to put CL in here for confidence level. And remember, in the z curve, 0 is in the middle. So we can make the margin of error smaller by making the z smaller by moving them closer to 0. But as you do that, you're losing area in the middle and you're decreasing your confidence level. So we could say something like, we state that we think the population proportion is in this interval, this really tiny interval, and we state it with 15% confidence. Nobody's going to believe anything that you state with 15% confidence. So I don't think it's a good trade-off to get a smaller margin of error by simply reducing the confidence level. So we're not going to shrink the confidence level to control the margin of error. But what about the standard error over here? Well, it's got two values inside of it, a p hat and an n. We can make the margin of error smaller by making the top of the fraction smaller. But we really have no control over what p hat equals. It is what it is. So again, we can only control the sample size. So what can we do to the sample size to cause the margin of error to shrink? Well, to cause the margin of error to shrink, we want this square root to shrink. And to make that shrink, we need to make the inside of it shrink. But what can you do in a fraction's denominator to make the fraction shrink? Make the denominator larger. So we seem to have some control over the sample size. A larger sample size makes for a smaller fraction, which makes for a smaller margin of error. Now, if you're really trying to break things, you could say something like, but, if we increase the sample size, we're changing the sample, and therefore we're going to change the sample's p hat, and we don't know what's going to happen up there. True to an extent. Increasing the sample size would change the value of p hat, but this numerator is not going to fluctuate much. I'm going to spare you the algebra, but because the p hats are only between 0 and 1, this numerator can only get so large or so small. In fact, I'll tell you right now, the smallest this numerator could be is 0, if p hat was 0 or if p hat was 1. But there is a cap on how large the numerator can get. Without going into the algebra, the largest the numerator can get is actually 0.25. And that's obtained when p hat is exactly 0.5. In other words, exactly 50% of the sample has a characteristic. If you're really curious as to the algebraic reason why the numerator of this can't get larger than 0.25, talk to me. But the sample size can just keep getting larger and larger. So we do have a lot of control over the margin of error by simply jacking up the sample size. So if we can do that, then why don't we solve this for n so that we can come up with a formula that says, here's how to calculate the sample size based on your margin of error, your p hat, and the z, which is a direct consequence of the confidence level. So let's solve this for n. I will not ask you to replicate what's about to happen, but as an algebraic exercise, it's not that bad. If I want to solve for n, the first thing I need to do is get rid of the square root. So I'm going to square both sides. I'm going to square the margin of error. I'm going to square the z, and when I square the square root, it will get rid of the square root. No more square root. Next, to get the n out of the denominator, I'm going to multiply both sides by n. That will make it cancel over there, and it will show up over here next to the squared margin of error. And that leaves us z squared times p hat times 1 minus p hat. And now to get the n by itself, I just have to divide both sides by the squared margin of error. And so the formula we get is n equals z squared on top, p hat on top, 1 minus p hat on top, and the squared margin of error on the bottom. Now, most of the time this will come out to be a decimal. It will hardly ever not be a decimal. So the same rule as before, always round up. You never round down. Always round up. Because if you round down, you're making the sample size smaller, which has the effect of making the margin of error larger, and we don't want to do that. Let me check the time on this video. I may pause and start another video for an example. It's only 5.5 minutes. If it's a long video, that's okay, because it'll be the last one. So for example, actually there will be another video out of necessity. Consider the previous problem, where we had 99.5% confidence level, CL for confidence level. Our p-hat was 0.326, I believe. And our sample size, well, we're not going to have the sample size. We need, because we're going to calculate the sample size. In the previous video, the margin of error was about 0.05. But let's answer the question, what sample size is needed to make the margin of error no more than, let's say 0.02. So we want a 2% margin of error in our calculations instead of a 5%. Well, we have a formula for that. It's sitting right here. Now, we weren't given the z, but we've already found the z. Recall that this 99.5% confidence level meant that z was 2.81, so there's no need to go and redo that again. In a problem existing on its own, you may have to calculate the z-score from the confidence level. That's okay. All right, let's set everything up. We square the z, so 2.81 squared. We multiply by the p-hat, 0.326. And then we multiply times 1 minus the p-hat. And in the denominator, we square the margin of error. So we're just doing this formula to those values. Be very careful using your calculator on this one. Watch your parentheses. Make sure you square the right things. 2.8. This calculator doesn't have a square button. It's okay, I can multiply it times itself. 2.81 squared times 0.326 times, doesn't have parentheses either, so I gotta actually do the subtraction. 0.674. 0.674 is the answer to the subtraction problem, divided by 0.02 squared. All right, I'm going to write down the exact value that I got. Well, it's an approximation. It might be the exact value. 4,337.4065. But that's not our sample size. We can't pick that many people. We have to round it to a whole number. Normally this would round down, but you always round sample size up when you're controlling margin of error. Because the relationship between the two variables is when one goes up, the other goes down. So if we round this sample size down, it's going to raise the margin of error up above 2%, and we don't want it to go above 2%. So you will never ever round the end down, you will always round it up. And in this case, it would normally round down, but we're going to round it up to 4,338. So with the sample size of 4,338 people, that would guarantee that our margin of error would not exceed 2%. Now, that's all there is in this section, so you might be wondering, why did you say there's going to be another video? Because there's an inherent problem here that we're going to fix. This problem is working on the presumption that we have not selected a sample yet, because we haven't chosen our sample size yet. But if we haven't selected a sample yet, how can we possibly have a value for sample proportion? How can we know what percent of the sample has a characteristic when we don't even know how big the sample is that we're going to pick yet? Well, you can say one of two things. Number one, you can use a p-hat based on a previously chosen sample. I could do that, but what if I don't have a previously chosen sample? Well, I'll tell you what to do in the next video.